The next speaker is Tanmoy Modak.
All right, so am I audible? Yep. All right, so I want to thank the organizer for giving me this wonderful opportunity to present my some very recent works. And my sincere apologies for those who are in IOP and had to listen this talk twice in 2 days. So today I'll talk about, so that the talk is same except the title is changed. Today I'll talk about inflationary landscape, basically how do I probe inflationary dynamics using future experiments. So mainly I'll focus about CMB experiment, and I'll focus about something called 21 centimeter intensity mapping. And I want to hear your comments if there is any for this kind of things. So cosmic inflation, and I don't have to probably introduce to the audience that cosmic inflation provides a unique solution for the so-called flatness, horizon, and exotic relic problems. So what these problems are, so our current universe appears to be very flat. So if we go back in time, universe is expanding. If we go back in time, the flatness will appear to be very, very precise, very, very small. Apparently, we don't know what should be the reason. Of course, universe can start in a very flat way, but we try to always find dynamical reason for anything that is, kind of this kind of small flat. Now, there is another problem, something called absence horizon problem. So, if you look at sky, like look at two distant patches of the sky, for example, CMB sky, if you look at the CMB anisotropy, which is separated by 1 degree angle today, at the time of their generation, they never had any causal contact. And the point is, if they never had any causal contact, they have an average temperature of 2.7 Kelvin. And the fluctuation, which is also quite similar in these two distant patches. So if you look at CMB, multiform, anything less than L equals to 200, they never had any causal contact. Now the question is, if something never had any causal contact, how the anisotropy as well as the average temperature could be same? We have no answer for that, standard cosmological understanding. And then early universe models predicts lots of exotic relics like magnetic monopoles, cosmic strings, and we don't see in our current epoch. Cosmic inflation provides a unique solution for all of these three things. So it basically exponential expansion epoch of universe. And if you have exponential expansion, for example, you can have arbitrary flatness and then inflation basically flatten it out. The horizon problem, the patches that appears causally disconnected, they had some origin at the early universe when they had causal contact, but universe expanded exponentially faster than the speed of light. And then basically you can have an explanation for this, why two causally disconnected patches have same kind of structure. What is the kind of way that we can have this kind of solution for this kind of things? That if you have a scalar field, there could be other types of field. If the scalar field is kind of slowly rolling to a potential, it will provide a constant energy density. And once it provides constant energy density, you can see that universe will expand. And in fact, we are currently experiencing exponential expansion. Of course, not in our local universe, but if you look at in large enough distances, you will see that universe is expanding, which is essentially dark energy. Now, cosmic inflation providing unique solutions for all these three things. It has some byproduct, very, very nice byproduct. So it produces some perturbation, quantum perturbation, and those perturbation you can construct something gauge invariant perturbation, and it can actually translate to something called curvature perturbation. And all this curvature perturbation can be imprinted in the matter distribution, essentially producing some perturbation in the matter distribution. And anything, if something is generated from this matter, they will have perturbation. So the large scale structures such as CMB temperature and polarization fluctuations, neutral hydrogen density, and which is translated to 21 centimeter brightness fluctuation, all these things will have this kind of information about this perturbation. As in, if we can measure this anisotropy, we can probe cosmic inflation. All right, so what are the models? As you can see here, there are many models, and they have picked, so this is a result from Planck 2018, and they have many results. So you can see the best result in the y-axis. This is something called tensor to scalar ratio. So basically, tensor amplitude divided by scalar amplitude, and this x-axis is basically called primordial tilt. If you want to construct an inflationary model, you have to stay in this shaded region. Either is red or blue. I think red is a little bit stronger. So it basically adds different polarization and temperature anisotropy, and also add BK15, which is 2015 data of bicep cake array, and baryonic acoustic oscillation data from slow and digital sky survey. And you can see that one of the models, so-called R-square inflation, is sitting exactly at the center here. If you have any inflationary model, all you want to do is just try to stay in this region so that you can explain cosmic inflation. But there is a caveat. This figure is generated for single field inflation. If you have two fields in your model, you cannot use this thing unless you kind of minimize your potential in one direction and have inflation happening in other direction. You cannot use this. So there is a caveat. All right. So now question is how we can improve our understanding about inflationary dynamics using future data. So I start with CMB, which is already well-known data. I don't want to go into detail. The temperature anisotropy and polarization anisotropy provides a very tantalizing proof for cosmic inflation. Of course, we have existing data for CMB of like Planck 2080, which is the legacy data. You can use it. It's a publicly available data. And there are two future experiments, which I will basically focus on mostly. CMB S4. So this is a ground-based CMB observatory based in South Pole and Chile's Atacama Desert. So there are 12 telescopes with 500,000 cryogenically cooled superconducting detectors, and it has excellent temperature and polarization sensitivity. And then you also have LightBird, which is a space-based CMB experiment run by Japan Space Agency JAXA. Both of them will start collecting data around the end of this decade, 2028, 29. And what scale that I'm looking at, you can see here for CMB S4, I'm looking for L equals to 30 to 3000, and you can see easily that it is going beyond Planck sensitivity. LightBird from 2 to 1350, but actually LightBird should stop here at 100 or so, and then combination in a mutually exclusive multiple range. 2 to 50 here and 50 to 3000 for LightBird low L and CMB S4 high L. And this is, we didn't do anything, we just took some likelihood, mock likelihood from these guys who provided some likelihood in their cosmic microstructure Monte Carlo kind of framework, and we just used their mock likelihood. There is another data, which is the so-called 21 centimeter intensity mapping, and we are targeting an experiment called square kilometer array. Most of you already probably know, it's a radio telescope. What exactly this 21 centimeter intensity mapping? As I already told, that this is a resonant interaction of CMB photons and the hyperfine transition. And you know hyperfine transition has a characteristic wavelength of 21 centimeter and frequency of 1420 megahertz. So if neutral hydrogen has some perturbation originating from the matter perturbation, and that can also be traced back to even earlier cosmic inflation, then if this hyperfine transition happen, either absorption or emission, this perturbation will be imprinted. And if you measure, this is called tomography, if you measure this 21 centimeter intensity mapping, you will have those information about those perturbations with bunch of caveats that there are a lot of astrophysical things and astrophysical uncertainties, which I'll point out in future. So what is actually measured is something called differential brightness temperature. Is this tau is optical depth, and the redshift range and the scale that we are targeting, optical depth is very, very thin. And this is basically TB is the brightness temperature, and T gamma is the CMB temperature, and this we have to divide by redshift because we are targeting at say, around 10 to 8 redshift. And the power spectrum is given here. So this is the mean differential brightness temperature. We just use the expression from this paper. However, we basically modeled in our, so this is targeted at some low redshift region, but we are targeting slightly higher redshift region. And so the power spectrum for 21 centimeter, this intensity mapping is given here. So there are a bunch of things, standard things, this Alcock-Paczynski effect, which is essentially finding out what is the difference between true and fiducial cosmology, resolution, this is connected to the detector effects and things, and then this apparent anisotropy generated from this redshift space distortion, like what you see in sky is not exactly there, so it's there's some gravitational lensing and stuff. Now, so to model these things, so basically essentially get this, what is this power spectrum, there is some biasing for the matter power spectrum requires. Here, this number is very, very complicated number. We have to use some information of some precursor of SK to get this thing, but here we just use as a nuisance parameter, just sample this BHI. There is another important thing, this gamma HI, which is this neutral hydrogen density fraction. This has also some uncertainties. For example, it has a quantity called neutral hydrogen fraction. And this is a very important thing because the parameter space that we are, or the target redshift range or scale we are targeting, neutral hydrogen is not 100%. So we cannot actually use 100% in this power spectrum as a neutral hydrogen. So to model that, we just basically targeted some fitting function in this here, and we used the public code called 21 centimeter fast. Use some cosmological standard lambda CDM parameter and astrophysical parameter, and we try to find out, if we just assume this kind of function, what is the values for these two parameters, lambda 1 and lambda. This again are nuisance parameter. Using 21 centimeter fast, we found two fit values, best fit values for this one, and we just use this best fit value as a fiducial value for our SK likelihood, and basically sample around them for as a nuisance parameter. So we have these three nuisance parameters in addition to all the other inflationary parameters that I will talk about for SK. All right, so the redshift range that we are targeting 8 to 10, and the scale that we are targeting 0.01 megaparsec inverse to 0.02 megaparsec inverse. And we believe that in this range, our physics will be linear, and we can actually prove cosmological perturbation or early universe inflation. And that the redshift range and the tomographic slice that we are talking about does not change our XH parameterization, that we have actually checked that our tomographic slices is something like 37.09 megaparsec H inverse. We use 20 beams, and the ionizing patches are few megaparsec. That means that the ionizing patches in the neutral hydrogen is very, very small. It essentially averages out. And this is the specification, and you can see that the frequency band we are targeting 50 to 350, and if we have 21 centimeter, which is 20 megahertz, so if you divide by 10, because that is the redshift, it will fall in this frequency band. And that is essentially the target for the SK low frequency part of the telescope, and this will be built in Australia. And the SK low have 224 stations, and each station will have 256 antennas. Each antenna will have 3.2 meter square diameter. And we have implemented in our noise modeling for that. I'm not showing the details. And compared to a similar type of experiment which is running now, is a LOFR, it has 25% better resolution, and it has the survey will be 135 times better. Now, what about the models? So first I talk about something, a very effective model parameterization. So if you do not believe in any model, so this is some effective model parameterization of inflation. So we take Hubble function and expand in Taylor expansion. And from that, this Hubble function goes in inflationary equation of motion. And if you use the data, you can automatically construct. And this parameterization is given in this paper. And Planck used this thing, so we just try to see that what we can do in a future experiment. And these are our model parameter, and remember for SK we have 3 biasing parameters as well, nuisance parameter as well. Now to show you how the sensitivity are, we use some Boltzmann code class and some Montevideo efficiency Markov chain framework. And for nonlinear matter power spectrum, we use halofit, and you can see the constraints. If you go in Planck 2018, this green shaded region are exactly reproduction of that thing. Now compare that to the light bar and CMB-S4, you can see that epsilon h, this is called fast Hubble slow roll parameter. And if you already heard about this thing, that we are these future experiments are targeting to probe so-called CMB B mode polarization, or so-called tensor to scalar ratio, which should be non-vanishing. And that will be a tantalizing probe for cosmic inflation, because that will basically provide a hint about that the tensor perturbation is generated during early universe, and inflation probably the source of that. And in a single field, this tensor to scalar ratio is 16 times epsilon h, and you can see if epsilon h is non-vanishing, that means that my tensor to scalar ratio will be non-vanishing. With if we add this light bar CMB-S4 this in a mutually exclusive way, you can see the constraint become much stronger, and if you add SK, you can see the constraint is even more stronger, which is expected. Then there are modified lambda CDM parameterization. This 6 parameter you already know, and then we added 2 additional running for spectral index, alpha s, beta s, and this R is tensor to scalar ratio. And for a popular model, like here I'm not showing the figure for Planck, you can, we have it. But we targeted a particular model like Stravinsky model, which is one of the best fit model to the data, and which is one of the simplest model to the data. And it produces a R tensor to scalar ratio about 2 times 10 to the power 3, and you can see that this future experiment can actually prove that. And then again, what I was talking about, the Stravinsky inflation, you can see here, pure Stravinsky inflation is extension of the Einstein gravity by this additional term with the associated coefficient m. And then we try to see that what we can do if we add an additional C term, R cube term in that. And you can see, depending on M and C, the potential shape changes, as in that the prediction for inflation will change. And this is the baseline model parameters given here. N star is something called number of if holdings before the reference mode exit horizon. Essentially, it tells how much time it takes to complete the inflation. Of course, it can run much early. The folding could be much early, but at least for the reference CME normalization scale, this is the kind of time that you require for inflation to last. All right, so what is the constraint? You can see the Planck constraint is shown here in the green shaded region. And based to our knowledge, we are the first people to actually do this. Not even Planck analysis, they have provided this thing. And you can see, I would like to draw your attention to M and C. You can see for C is kindly consistent with 0, but it has a positive bias. So if we take Planck's base fit value for our analysis and try to see what is the future sensitivity, you can see that future light band and CMBS4 can have rightfully 2 sigma kind of non-vanishing value. And if you combine all of these three things, light band, low L, CMBS4, high L and SK, it will have kind of 5 sigma kind of discovery. But again, there is a caveat. I assume that Planck's base fit value is realized in nature, which may not be true. So here you can see that exact normalized, the posterior distribution value with 1 sigma error bar here. And there are some caveats for SK, because this is the likelihood that we provided, although we have not made it plug in. If you need it, you can contact me. SK has a bunch of uncertainties because it's a load redshift measurement. There are many astrophysical things that might ruin our analysis. The biasing, this BHI that I talked about, whether the biasing modeling scar we just use as a nuisance parameter, probably a better modeling of the biasing parameter is needed. The neutral hydrogen fraction, as you already know, JWST, James Webb Space Telescope is observing some high redshift galaxies, and if you have high redshift galaxies, you need to change your also biasing for the neutral hydrogen distribution, and then your basically gas will be reionized due to the presence of high redshift galaxies. And then foreground removal. So we have foreground is much higher for SK. So we assumed spectrally smooth foreground, which can be removed completely. But there are some caveats. For example, if you look at the frequency band 50 to 350, the lower frequency band 50, there is some issues with the foreground removal. And so again, we have to use probably some nuisance parameter for that. So if you include all these uncertainties into account, so the Markov chain never converges. With our simplest thing, it took 10 days to get a covariance matrix and 15 days to get proper, marginalized posterior distribution. So if you include all these things, practically impossible, and nobody is doing that. People are using machine learning techniques, and we are kind of doing that to improve this analysis. And so that's it. So what I discussed, many models of inflation exist, and it's a very interesting paradigm to explain some of the open questions early universe. Future CMB experiment will provide a very sensitive probe with a bunch of caveats. SK will also provide a sensitive probe, and hopefully in coming end of this decade or maybe beginning of this decade, we might observe some CMB B mode polarization or non-vanishing tensor to scalar ratio. Okay, thank you for your attention.
So, yeah.
So the parameterization for the Hubble that you did in a kind of power series kind of expansion, that assumes an analytic function of phi, right? The Hubble is an analytic function of phi.
It assumes the analytic function of phi. Not only that, there are a bunch of continuity tests and things you have to do. Yeah.
Also, but in the at first you showed a Planck data which rules out some models. Like there were potentials where V phi is kind of phi power 4 by 3. So this could not be, this is any arbitrary model. So this will give a V phi versus phi as in a numerical way. So that doesn't depend on phi to the power 3 or phi to the power 4 or this kind of thing. This is specific model. So that I talked about two things. One is effective model parameterization that you can use, or you can use the same framework and you can take a specific model and feed it. These are specific model that they feed it. They actually didn't feed it. They assume that the inflation is only driven by one field, and in our nature there is only one field, which is not true. You have Higgs field.
if you have that and then you calculate, you take a derivative of the potential, you can calculate Ns and R, and you basically try to see what is the value of Ns and R to satisfy your, what is the reference mode, exit or horizon, which point, and then you can calculate Ns and R, and you can see that what is the value here. If you're sitting here, then you are fine. If you're sitting outside, you are gone.
So right, so that expansion can't be used for V when it's like 5 power 4 by 3, right?
Any you can use it. What's the problem with that? So this
Like,
that is a particular model. You have to implement that. You have to basically solve equation of motion, and you can assume slow roll approximation, can calculate it. This only assume not slow roll approximation. It just assumes slow roll parameter. Once it is 1, the epsilon h is 1, then inflation stop. It doesn't assume any slow roll approximation. It just assume that the slow roll parameter when epsilon h is 1.
Yeah, so okay. I was thinking like if V phi is non-analytic, then won't H would also be non-analytic, and that we cannot.
What do you mean by non-analytic?
Like analytic means phi
A particular form of the function, right? So you have a particular form of the function.
Yeah, so 5 power 4 by 3 is non-analytic, right? At phi equals to 0.
No, yeah. So okay, now you are asking some more detailed questions. What is the origin of phi? So these are kind of arbitrary potential that people use. So, and that's I also do not maybe prefer that way. You have to find a particular model for that. But if you have that particular potential and you assume that there are some convexity and this kind of test that you have to do, so you have to assume those kind of things and then basically solve your inflationary equation of motion, and then if you fits it. If it doesn't fit, throw it away. This does not assume any of those. This just assumes that I have an arbitrary potential. Hubble function is proportional to potential. If you have this Hubble function, then this Hubble function goes in equation of motion. How you actually reconstruct the potential from this one. That's it, nothing else.
Okay, thanks.